Now we're going to look at the role of wind in creating various landscapes and landforms. So we're going to look at wind processes, which are also known as Aeolian processes, and that comes from the Greek ruler of the winds, Aeolus. So we're going to continue to look at, just like we did with fluvial processes, at erosion, transportation, and deposition. So once again, we've got this predictable pattern of weathering, which then leads to erosion, transportation, and deposition. This time we're focusing in on the work of wind or moving air. So we're going to see once again a lot of similarities with fluvial processes, but as far as its power, its might, nothing like what we see with water and ice. And so fluvial processes, glacial processes, those are going to be our big-time landform changers. However, as we'll showcase in the following slides and images, Aeolian processes do leave their impact for sure as well. And so one of the things we're going to look at is why we see wind processes a little bit more prevalent, a little bit more as far as an influencer in arid areas, places that are quite dry. And this makes a lot of sense. Without vegetation, once again, vegetation, what it does is it holds the sediment in, very much what we can think of as grass, trees, whatever. When that vegetation is removed, it allows Aeolian process to then move that sediment from one place to the next. And like I said, we're going to see a lot of similarities with fluvial processes when we look at the Aeolian processes on the following images. Now let's look at the role of deflation. So deflation is very comparable to hydraulic action when we use that term to describe erosion due to fluvial processes in the previous video. But deflation, key here is removal and lifting of loose, typically weathered particles. And so because wind processes aren't as powerful, it's only going to be loose material, lighter material, sediment that can actually be carried aloft. And so key here is having that loose. It's not going to break away a solid chunk of rock just simply from moving air. Other processes, other erosion processes are at work. But when it's loose, then a little bit more chance of deflation occurs, especially the smaller the size. And so once again, we see the idea of removal of vegetation in grassland areas likely lead to deflation of sediment, to actually use that term kind of in a sentence. So one of the things we see deserts, surrounding deserts, the peripheral areas around deserts, we see what we call desertification. So essentially the idea is that the deserts of the world are getting bigger. What's causing them to get bigger? Well, that key area that is the transition from desert to forest, typically we see a grassland area, i.e. tropical savanna. Well, what's happening is the deserts are getting bigger as that grassland area is being removed for various reasons, largely due to increased population growth, which is putting stresses on that transition zone from desert to forest. And so one of the key concerns is desertification, because what's that then do? It increases the likelihood of dust storms. It increases the likelihood of an area essentially becoming useless agriculturally. So it's a term we're going to come back to in human impact on the environment lectures at the end of this course. Finally, to get a little bit more domestic application of this topic, and that's the role of off-road vehicles in Utah. And so Moab, Utah is a destination. It's a key destination for people to drive ATVs, four-wheelers, three-wheelers, whatever, out in the countryside. So one of the things that's occurring is trails are developing. Trails in which, I love driving cars, and trails in which off-roaders are using to fly through the desert for recreational purposes. But what's that doing is that's increasing deflation. It's increasing the likelihood of deflation. So this is becoming more of a concern in Utah as people are a little bit more aware of the impact of this industry, tourism, recreation, and its role locally regarding sustainability. Is this a good idea for long term, and what are ways we can mitigate or lessen the impact of these vehicles? Here we see an area from southern Utah. So one of the things we look at this landscape, what created it? Why does it look the way it does? Why do we have the Three Stooges here that are kind of remaining over time? Well, first off, we have to understand that this whole area, what we see here, was at one time one massive slab of rock. So over time, Aeolian processes have removed a lot of that rock. And so what we can see in the upper image there, the upper graph, those diagonal lines is essentially what has been weathered away, eroded away, removed from the area, so that all that remains are the Three Stooges here. So essentially what we got going on are the Three Stooges, these three large pillars of rock, are hardy, sturdy, solid rock, the Chuck Norrises of rock. And over time, they've been able to resist weathering and erosion, but eventually they will also eventually weather and erode away themselves. But this is once again time, millennia. Takes a long, long time for this rock to then weather and erode away. Here we see one of the oldest structures on Earth, on our Earth's surface, and that's Uluru, or Ayers Rock. Uluru is in Australia. It's a very key point for Aboriginal culture. I'll let you read up on all of that. But what we have here is a monolith. So essentially what this is just this chunk of rock that over time has been able to withstand weathering and erosion. If we kind of think about this image, the image on the following slide, the image on the previous slide, these are all in quite dry areas. And so once again, we're going to see these processes, Aeolian processes, more at work in arid and dry areas like the outback in Australia. Here we have Devil's Tower, a massive structure somewhere out in California, Nevada, somewhere out there. But anyway, so here we've got this interesting structure. Well, what the heck has created this structure? It's this tall tower in which it almost has this flat top. If you look at the top, you could almost climb up to the top and, maybe, I don't know, play some beanbags or cornhole up at the top. Well, legend would say that a big, massive bear tried to climb up to the top to chase these Indians and scraped away the sides of this mountain structure, whatever, and creating this very much this Devil's Tower. Not the case. The Devil's Tower is the size much bigger than just a bear, and so this is the Godzilla of bears. So this is not true as far as how it formed. Not the nails from a giant bear. Instead, this is how Devil's Tower formed. And so we can think back, western part of the United States, we're going to get some converging plates. So we're going to get more chances for volcanic eruptions, volcanic systems. Okay, we know that. Well, if we can go way back in time, what ended up happening was this area was this one huge chunk of rock. But over time, a magma plume started to come up through underground through the lithosphere and was almost poking through the surface. What we call this is a volcanic plug, because what ended up happening is this volcano never made it to the surface. So essentially it petered out, it dried out, and so over time this magma, this volcanic plume, hardens, forming this igneous rock. And so essentially igneous rock that's surrounded by a totally different other type of rock. So this is largely, knowing this area, largely a sedimentary rock that we see overlying this volcanic plug. Then over time, Aeolian processes go to work and slowly remove that sedimentary rock. Slowly, millennia, lots of time, till we get to the point of what's still revealing. Devil's Tower is essentially that volcanic plug in which Aeolian processes have removed the rock around there, and so this Devil's Tower it's hardy rock. It's weathered. It's very much resistant to weathering and erosion. So it's been able to withstand the weathering and erosion. So it remains this tall structure that we call once again a volcanic plug for the 30th time.